Hello, everyone. Today, I'm going to talk about a tool that I recently developed called the Accurate Water Property Simulator. In short, it's called AWPS. And this tool is being designed to calculate the water properties using one of the four methods that I developed to accurate capture or do the uncertain quantifications of the properties of nano-confined water. So the terminal is showing here, and it is developed using the Python language. And if I run this program, it will tell you, welcome to the accurate water property simulator. And please enter the following dimensions of a desired water box. So from here, I will give you some uh, background of how this program works. So let's take a look at uh, let's take a look at the node. So the workflow here is the program will basically allow the users to randomly select solid materials. So no matter what your solid material is, you just input uh, two walls at one is at the bottom, the other is at top to create the nano-confined environment for the water molecules. And the first step I just introduced is to design a water box that has the desired dimension and the densities of the water in your simulation. And here is showing by using the black body shape here. And we also want to, after we have that water box, we want to add the solid walls on top and on bottom of that water box. So let's go back to our uh, terminal. So for example, here, if I want to enter the water box in X dimension, the unit is in angstrom, it's 40 by 40 for the cross section. And here you want to note that in order to properly put the water box in between our two solid walls, I have to make the Z dimension of the water box to be 4 angstrom smaller than the actual separation of the solid walls. So I will pick a number here. So next I will enter the water density. For example, if I want the water density to be 0.9, I can enter this number and hit enter. Then the program will go ahead and generate a water box using the PECMO to get a PDB data file. And from that PDB to a LAMPS data file using the mode template. And after getting the mode template, it just what this step is using running lamps to do the energy minimization of that water box to get optimized structure in order to start our MD simulation. You can see after that many steps, the energy has been minimized to a reasonable number instead of very high energy to start our simulation. And so you see here, we have the info printed. Congratulations, now the simulation structure is ready. Please choose a method to measure the water properties. Now I currently developed the full accurate method for the diffusivity, but later on I want to put a placeholder for the other water properties such as the viscosity and thermal conductivity. So here, if you don't know what to enter, you can just enter help. It will tell you that you can only choose from the following method: hot code, seize, no stop, and unscrambled. This is what I call the full method that I developed now. And for example, if I enter seize means running 50 random seize and get the average. And then the simulation will basically start to run. So let's just stop that simulation and see what actually is happening. So if I check which directory is the newest created, I can see that the water dash 708 is the newest directory, which means I just created that folder. So the water dash means how many water molecules are in that water box. So that is based on your input of the XYZ dimension and the density of the water molecules. Basically, you can get this number. In order to make each directory distinct from each other, I will choose the number to be the distinct properties of that directory. So we will go ahead and see what are inside of that directory. So if I check, basically there are all the necessary data files to in order to for the PACMO and more template to work to build for these data structures in order to make our simulation to run. And what we just choose was a random seed method. So let's see what's in there. So I have a LAMP script that had 50 random seeds, and each time I just call random seed and get the water properties, in this case, the density, and then I quit this loop to get a second random seed, and this is how that method work. And after that, I will get 50 MSD curves, and what I do next is I average these MSD curves and get a standard deviation to see what to do the uncertainty analysis. And you can basically randomly choose other three methods that I developed here. Uh, One is called scramble, the other is called unscrambled. So the difference here is whether you have the high temperature running during your simulation. And the other one is basically serial measurement, which means you don't have any waiting time in between the 15 measurements. And you can also uh, so this program also allow the user to input how many groups you want to run, you want to run in these simulations. So if you're curious about uh, how some of the details, I can also share some of the info, uh, basically about how I calculate, for example, the density of that water box. Mm, so if we recall that, uh, if we, uh, just a minute, I will pull out the note. So if we recall how to calculate the water densities in the nano-confined environment, it's basically the mass over volume. And the mass is determined by the number of molecules times the molecular weight of the water and divided by Avogadro number. And the volume is the actual volume that can take by the water molecules, because we have to consider the excluded volume, some of the distance that the water molecules can no longer approach in the solid walls. And it turns out to be, if you solve that equation, setting a density to be 1 grams per centimeter cube, the number of density will come out to be that expression. If we set the number of water molecules to be a factor times the actual volume, then the factor is expected to have a unit of angstrom squared. Uh, so the unit of this factor is expected to have that unit. And when the density is 1 grams per centimeter cube, the factor came out to be 0.03344. And I just take this number to accommodate for different water densities in our simulation. Okay, so that's all I want to say about that structure. Thank you.